today we're going to continue with the second talk. The talk is going to be on Shannon's theorem and polar codes, from theoretical limits to practical encoding. Here we have Ali Assaf, who's going to talk to us about it.
Hello, everybody. Welcome to my presentation. And polar codes are a very interesting thing. The agenda we're going to have is we're going to first explain some core concepts behind communication theory and how we communicate between two different nodes through our channel. And then we're going to define Shannon's theorem, why it's so revolutionary and what it brought about. Lastly, we'll do a brief introduction of polar codes and their base construction. So to start off, the core concepts. Communication has been vital for humanity since the dawn of time. We started off with sculptures, with paintings. We moved on to language and communication with the signals over the air. And lastly, we had telephone communications with digital signals and like wireless. These new technologies are all brought about by signals and systems. Signals are everywhere. This is simply communicating the signal of sound over the air. This digital signals electricity moving through wire. But they all have one common problem, and that is errors and noise. With the sculptures, you will have them weathering over time. With the people's language, you can have them accidentally say the wrong word or mess up with their tongues, or even just have some other noise interfering with it so you can't hear it. And you have interference with digital signals. So we're going to do a basic simulation of communication to give you an understanding of how this works. Alice wants to tell Bob that want to play basketball now. Okay? Where each word here is modeled as a symbol. So she passes it through a channel, and what the channel's purpose is to model errors. So what comes out of the other side of the channel is wanna pray basketball bow. So this is the message she's sending, and this is the message received, with no encoding, no nothing. It's just raw sending to a channel. Now, this is complete nonsense. We don't want this. So what's the solution, right? Well, what we've learned so far is message. We've learned on messages, it's just a sequence of symbols, where these symbols come from some fixed alphabet. In the case of Alice, this is consisting of 4 symbols, so we will define the variable k as the length of our message, which is 4. We also learned about the notion of a channel. A channel is just a mathematical model describing how noise occurs in real life. So it's usually a set of inputs and outputs that are also finite, where there's a probabilistic function that maps the input to the output, where it like distorts it in some way that would simulate reality. For example, this is what we did. We added some errors using the channel to our encoded message. Now, this is the solution. Do you want to play basketball now? We want to encode it in a way so that Bob can understand it even though there's error. So we introduced the notion of a coding scheme, where we have an encoding function and a decoding function. Alice tells Bob in advance, okay, I'm going to repeat each symbol 3 times before sending it across the channel. That's her encoding function. Bob's decoding function is he's going to group every 3 symbols and proceed to find the most common symbol that occurs and take that as the final. So if we simulate it right here, you can see as it passes through, even though there are errors in the final message, right, we can decode it and correct it. So Bob, even though he has errors and noise to the channel, he receives the correct idea. Next, we got to introduce this notion of the information rate, right? So the information rate, as we've seen from this example, we unfortunately had to multiply the size of our message that we're sending by 3 times, which is very, very inefficient. So the error rate is a measure of a coding schema of how much of this message that I'm sending through the channel is actual useful information and how much of it is redundancy. Because in here we repeated it several times. So in our case, the total length was 12 symbols, and the initial was 4. Remember these two variables here, they will come in useful. K is the length of the message, N is the length of the code word. Now, what is a code word? A code word is a sequence of symbols as well, but the difference is that our example here, 101, play basketball, blah, 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 okay, that is our code word, and it's mapped directly, is created from the original message. Now, you might think, okay, if we have more symbols, won't we have more possibilities of different symbols to have more, like a larger set of possible code words? The answer is no, because code words, they are functions of our message, which means that they'll always have the same number of possible code words as the same number of possible messages. This is a key idea you need to remember. Okay. Lastly, hopefully, we have our error correcting code. This essentially is just a schema and a way that we can transmit messages across channels without error, even though without muddling it up on the other end while we still have error to the channel. Now we have a good idea of how people communicate using digital systems. We can do some formal definitions of things we're going to need later on. So firstly, one type of channel is the binary symmetric channel. This essentially is just some channel where the input and output alphabets are both the binary digits 0 and 1. That's it, very simple. And the probabilistic function we use is just a Bernoulli random variable, which if you don't know what that is, don't worry. Imagine a coin flip, right? There are two possible outcomes, either heads or tails, or in our case, either there's an error or there is no error. This is essentially the idea behind the binary symmetric channel. Either we have an input 0, it's a probability P that we go, it flips and it goes to 1, which is an error. Same with the 1. So essentially, each symbol is probability of flip. That's it. Now I have a quick question for you all to test your knowledge. What is the probability that this input turns into that output? What's the probability you have this exact set of digits? Try and think of it one by one. Anybody know? Think Omar does.
Do I?
Yeah.
So I think you have two flips.
Yeah.
Each one of them is P.
Yes.
So that's P squared.
Yeah.
And then you have 5, which were not flipped.
Mm-hmm.
So I'm guessing that's 1 minus P
To the
5
power.
times. Yeah.
Okay.
So to the power.
Yeah. So if we go one by one, 1 minus P times 1 minus P plus 1 minus P times P times 1 minus P times 1 minus P times P. That's basically it. It's just drawing probability. There's the answer. Okay. Now onto the last couple definitions. Promise, almost over. Our Hamming weight is essentially a very simple concept. It's just the number of ones inside of any sequence of symbols. And our Hamming distance is the number of difference between the two code words. So if I had these two messages, let's say, okay, the weight of X will simply just be 2 because it's X. The distance will just be 1 because there's only one difference here in the second position. Okay, now we can introduce the coding problem. So in an error-free world, it's very obvious that we won't have to worry about it. We can just have a maximum rate of transfer. Remember, rate of transfer is the K over N, the number of information bits divided by the total number of bits. We can have an efficiency of 1. It's perfect. 100% of the information we're sending is real information. But in reality, that's not the case. We have noise. We have errors. And that's exactly what the coding problem aims to solve. Now, our problem now is if we try to introduce redundant values, then we're going to be having not only a reduced rate, but we're going to have increased reliability. But there's like a balance between the two. As we add more redundancy, we get more reliability, but our code becomes way less efficient. So that's the coding problem trying to balance it. So it's very natural to us why maximizing R increases the efficiency. It's just because we get more bits, right? They're actually real. But why does it also reduce reliability? You know, looking at it from like a mathematical perspective, it doesn't make sense. But remember that notion of Hamming distance I introduced earlier? Well, the minimum Hamming distance also decreases whenever we reduce the amount of redundancy we have, whenever we try and send more information. That's the key issue here. So to help you understand what minimum distance is, okay, imagine a Hamming space, right? It's just a box of a bunch of points. And each one of these points represents a code word, a unique code word, right? So now let's also introduce some abstract code. We don't care what it is. This is an example of the repetition coding we did at the very beginning. It could work. We have some encoding function, we have some decoding function. More specifically, the decoding function is minimum distance decoding, which you'll understand shortly. Let's say we have some message M, and we apply our encoding function to it to obtain E of M. Then we transmit that through some channel, and we're going to obtain a code word Y. So this is the original, and this is the received. Next, let's draw a ball around these points of radius Pn. Now, Pn here represents the expected number of errors, the expected distance from the original point that Y will be at. And for you who like maths, we know that this is going to be a very nice clean circle, not fuzzy, because by the Chernoff bounds, if n is large. Next, we're going to do the same thing for Y. And now I can explain minimum distance decoding. So the way that we're going to decode Y and find out what the original message was, is we're going to look at what is the closest code word to Y. Then we're going to set Y to that code word and decode it. Now remember earlier when I told you that even though you increase the number of possible symbols, you don't increase the number of symbols. You don't increase the size of the set of all codes. Remember that. So that means not every code word can be decoded back into the original message, which is why we set it back to its original state, what we think it is. Now you can see the problem here. If the distance between two potential code words, by the way, this is some other code word. We don't know what it is. We don't care. It's in the same Hamming space that I introduced earlier. So if we try and decode this, we might accidentally end up here, which is an issue, because then we're going to decode the wrong message. So we want to maximize the distance between these two code words. Now, intuitively, if you try and increase k while keeping n the same, what you're essentially doing is you're increasing the number of dots inside of the Hamming space, because in binary at least, the number of possible code words would be 2 to the power of k. So if you increase k, you increase the number of code words, so they're more densely packed, meaning that you would have way more of these within the same space. So it's way more likely for a small error. Yeah?
I just had a small question. So how are you measuring the distance between E of M and Y?
This is just the distance. Remember the definition for Hamming distance that we gave previously?
Ah.
Yeah, it's the number of differences between the bits.
So you start with the encoded message, and then there are some differences.
Yes. Correct.
Now another question. You said so it's almost surely within radius p times n.
Yes.
So why is this obvious?
You
have a coin flip here.
We flip a coin 100 times, right? You're going to get a value in between 45 and 50, somewhere around that, yeah? The larger we go, the closer it's going to be to the halfway. But you're very, very unlikely to get 30 and 70, for example. That's like almost impossible. The more number of flips you have. That's the idea. That's why it's such a better time.
And in that case, the radius is 50?
The radius in this case would be, it would be 50, yeah. That'll be the radius, because your probability is 0.5 and
the number.
Yeah. Now we can move on to Shannon's theorem, finally. So there was a problem, right? The engineers were trying to play around with these values, K and N, make up different decoding algorithms, but in reality, they didn't really have a concrete set of rules or anything that on how to make these codes. I'm not saying Shannon did that, he did not. But Shannon did do something else. He asked a very, very important question. What is the theoretical limit to the value R for every channel? Right? What's the highest it can be? Because we don't know that. But before we begin, we need to also introduce some of his concepts that he introduced in his 1948 paper, where he also included this theory, which is, firstly, information. If I asked you to quantify a piece of information, like the sky is blue, right? How would you do that? Nobody, you can't think of, yeah? You can hear?
I can't think of it.
No. But Shannon found a way to do that. The way he did that was he defined some axioms for information. Like, what do we know about information? Well, if I walk out every day and I look up and I see the sky is blue every single day, I'm going to be expecting it to be blue. So the probability of it being blue is very high. So when I walk out and I see another blue day, oh, no new information because it's almost guaranteed. I move on. But one day I look and the sky is red and I'm like, oh, that is cool. That's going to be some new information, right? And I'm like, well, why is that happening? The day was once red. And so this is exactly the idea that Shannon was trying to portray. This surprise factor. The second axiom, which comes naturally from this, is that the probability of an event increases, becomes more guaranteed, you have less information about it. The last property, which is more mathematical, is that information should be additive for independent random variables, which means that, okay, if I have two random variables that occur separately, right? I measure here and measure here. The total information I should get from both of them should be just the sum. Simple. And turns out somehow the log function here matches all of those properties perfectly. And that's why the information content of some random variable is formally defined as log of 1 over p. Now, some of you might ask about the base here. The base basically just changes the unit of information you're working with. In our case, it's 2, so our unit is nats or Shannons. And if it was E, for example, our base unit would be nats. But in hindsight, this changes nothing about what's coming next. Nicely. Next, we can move on to the concept of mutual information. Let's say these two random variables are dependent, not independent, right? That means if I observe X, I have some idea of what Y could be. So mutual information has this idea of the amount of new information we have about X given that we have Y. Right? Now let's say I have an input X, and I pass it to the channel, and I have an output Y. Okay? Given that I observe Y, how much information do I know about X? This brings us to the idea of capacity. Okay, capacity is how much information, the maximum amount I can get out of my output Y, that'll tell me about X. By the way, this very important note is separate from Shannon's maximum capacity. We have not linked it to rate at all yet. Right now, it's just an abstract, independent concept. Last thing I want to introduce to you guys is the notion of entropy, which in essence is if any of you have taken statistics, you would know that this looks kind of similar to the average value you get out of some probabilistic function, some random variable, right? Which is just multiplying the probability by the function here, which in this case, the function is the information. So we can say that entropy is the average information content. Simply put, like that. But we can also say it's the amount of uncertainty we have about this random variable. So if you think of a uniform distribution, PMF, right, probability mass function, and you think of all the probabilities of the events, if one probability is very likely and the rest are almost zero, it's going to have zero entropy because it's not random at all. Entropy measures like the randomness of a random variable. Now we can finally introduce Shannon's theorem. Shannon's theorem states that for every channel, there exists some threshold C, which is the channel maximum capacity, or just channel capacity, such that one may always reliably send information across a channel with no errors on the other end, so long as they maintain the rate R below this capacity. But the converse is also true. If my rate is slightly above this capacity, if by a little bit, my error probability will just skyrocket. So meaning that, if I'm below the channel capacity, I can always transmit reliably. By reliably, I mean there will be no decoding errors, or virtually none. Hence, the probability tends towards zero. And the other end, if I'm above it, I can never transmit codes. And in our specific case for binary symmetric channels, which we mentioned earlier, the channel capacity is defined as 1 minus HFP. You might be wondering, how did we come about this? Where did this come from? Well, we know that h of x is the average information, right? But so you might think, oh, do we want more information? Or shouldn't it be just h of p? But no, it's not the case. Remember, it's also the average uncertainty because we're measuring on the probability of error, p. So we are looking for the average certainty. So the same way that we found the probability of it not being an error as 1 minus p, we find the capacity 1 minus h. What happened? Nobody can use this. Nothing happened for 60 years. The problem is that the Shannon's theorem is non-constructive. Okay, it did not give us any explicit way to make a code. It just said, this is the best you can make. So now we move on to polar codes. The first code to mathematically provably, actually reach Shannon's capacity, right? And now we're going to go on to why making this so great and how to construct it. So there have been attempts over the years to make capacity achieving codes like turbo codes and LDPC codes. But then Arikan in 2008, he introduced the first probability efficient method. Nowadays, they are commonly used in 5G technologies and they're a very promising candidate in 6G technologies. And the main idea is that given some message here, okay, I'm transmitting information, actual K bits, over these black bits here. These are the good bits. But some bits are frozen. So these zeros here, they're frozen. They're always going to be set to 0. And the reason why this is because each bit treated as its own binary symmetric channel, right? This one has a very low probability, very high probability of error. This 4 here have a very low probability of error, so they're much more reliable. And this might seem confusing, like how can this message have different probabilities for each bit? And that's what we're going to explain now. Okay. So how were they created? Arikan first said, okay, let me take 2 bits, U and V. I'm going to take the XOR operation of them because I'm trying to compress them, right? But then he realized, okay, I'm not actually compressing them because I'm losing information. So instead he tacked on a second bit, V. So now he encoded U and V as U plus U XOR V and V, which is a reversible operation if I just take the XOR between these two again, and I'll get U. So we can see that the probability, like what he found was very, very cool, that the entropy actually shifts. What I mean is the probability, sorry. So probability of U plus V having an error increases while V decreases. And when does this error happen? Okay, specific scenario, in specifically U plus V. We'll think about just this.
I'm sorry to interrupt you here. I just have a small question.
Yes.
So in the previous slide, why is it relevant for us that the error probability shifts? Why is this useful?
Because as I outlined in the previous slide, over here we have these bits which have a very low probability of error, and these bits have a very high probability of error. And we're going to show you how we brought it out to be like that, how we've encoded it in a way that this information can be experienced in that way.
So very, very low is like close to 0.
Yes.
So in a way, this code then, the frozen bits are chosen after the process has been done.
Yes. Yeah. Exactly.
And now you're going to show us how to do the process.
Yes, precisely. We're going to find a set of indices They're going to show us which ones are frozen. Okay. Okay, let's look at it case by case. Firstly, let's look at the U plus V bit. This error only happens if one or the other bit shifts, not if both of them shift. Because if both of them shift, if we look here, shifts to 1, 1, same thing. Shifts from here to here, same output. So it's fine. But if one of them flips, then we'll have a different output. So we can say that, okay, it's the sum of one having the joint probability of one having an error and one not having an error. So we can say it's 2p of 1 minus p, which we can see is greater than p, so long as the probability p is less than half. Next, we're going to introduce the v. We're going to explain why that decreases. Well, we're going to use the idea of entropy here. So first note that the entropy after is the same as the entropy before, which is just 2 times the total entropy. Because each variable is initially independent, we can easily calculate the entropy as just like capital H of V. And when we double that, we're adding it to H of U, but because they have their independent variables intersect, not dependent, there's no conditional entropy yet. Once we introduce the chain rule of entropy here, we see that, okay, now there is some conditional probability. And lastly, we can rearrange the chain rule of entropy simply, and we obtain this very, very nice equation, which basically lets us know that, okay, so long as p is less than a half, 2h of p minus h of p prime is the probability we just finished calculating, is going to be greater than h of p. So because the entropy randomness increases, we know that the probability decreases. Remember the inverse relationship. Lastly, this is just like a summary of what we've done so far. So we can skip it. But the key idea we want to get you in mind is we want the channel capacity of each sub-channel. We're treating each bit as a sub-channel, by the way. We want to polarize it to either be maximum or minimum. So now that we've done it to just 2 bits, we want to expand this. How can you do it to a whole message, right? So given some message m, which is 4 bits long, right? We want to make log base 2 of n copies. Sorry, that should be 2 to the power of k copies. My bad. So we basically duplicate it however many times it's gonna. Then we're gonna pair up each bit. So simulation of that would look something like this, where we have this 4-bit message, this 4-bit message. Then we take the first 2 bits, we're gonna encode them. Then we take the first 2 bits of the second part here, and we're gonna encode them as well. Then we're gonna separate out these 2 groups here and here, the U, the XOR group, and put them in their own little tiny group. So it's gonna look like this, and it's gonna look like this. This is with respect to their order. Then we're gonna be applying this algorithm recursively to each mini group, where each mini group is halving in size each time. So given this massive, it's not really that massive, recursive algorithm, we can finally keep going until we're left with a group that's just one bit. There's only 1 bit there. And we can test the entropy of this this bit, or the, let's just say, probability to keep it simple, and keep it. Yeah, so we can test the probability, and we can know if it's really high or really low. If it's really high, we mark it as a really bad bit, a frozen bit. And if it's really low, then we put it in our set of indices for the good bits. And basically, that's the algorithm complete. So, quick summary, we apply local polarization recursively for every single bit. It has a fixed number of steps because we know that the size of the group halves each time until it reaches 1. And channels with low entropy, which means that they have a high probability, is going to be 0, which is going to be reversed. But yeah, so far we've explored coding theory and the schema for transmission signals. Then we've explored the idea of simply just Shannon's theorem and how he got about to it, an idea of information being quantified as a value, which is really, really cool. And lastly, we explored polar codes and how they construct. Shannon showed us this can be possible. Arikan gave us a practical way to do it, and now they both unlocked a future of new discoveries, 5G, 6G. Thank you all very much for my presentation, and if you have any questions, I welcome.
So I have two questions. So first of all, if you can come back to where you were, like you did 2 to the power k copies.
2 to the power k copies.
Yeah. Okay. I think just felt a bit confused. How? Okay, so you made 2 to the power k copies. Where does the V1 distribution come from?
Oh no. This is the original message. This is just one other copy.
Okay, so why don't you 2 to the power k copies?
Because I made a mistake in the presentation.
No, why 2 to the power k? Like you said, it's
It's because if you paired each bit up individually, right? You're gonna have the size, right, of the message base, right? Because if I have like a whiteboard or something,
you can write it.
Where?
Okay, there only has
How do I?
They take the pen, I think. No, it's
I remember them doing it. Okay, Nes, I'll try and explain it to you.
Yes, what's
So it's working?
I don't say it's.
My board is better. Oh, I turned it off.
That's why I don't say it's.
It's fine, it's fine. Okay.
Did you lose? It's no pen there?
I think it's loading. But basically, because we pair up each bit, let's say we took log 2 of it. Okay, we took only 2 groups. If we did that, then if we paired them up, it'll have only twice. So we'll still have 2 groups of 2 bits each, which isn't gonna work. So if we take 2 to the power of 4 groups, right? Keep grouping, splitting, then you're gonna have to run the algorithm by hand to like better understand it. Yeah, it'll just be like that.
Okay, and the second question was that, okay, so now you said that using the power codes, we could achieve what was said by the Shannon, basically. Does that mean that, okay, so we have officially reached our limit?
No, because even though the limit, yes, it is reached maximum capacity, which is very nice. This is just one of many possible algorithms. We don't know what other algorithms are abstract we can come up with. But the problems like with polar codes is mainly because it's a recursive algorithm. Also, the number of steps is known. Yeah, exactly. It takes a lot of time to first set it up and then find the indices and then code it and transmit like that. Whereas there are some other codes like LDPC codes, or turbo codes, which are known for being called turbo codes, which are known for being like lightning fast. Even though they don't achieve channel capacity, they're very efficient if they're running on lower end hardware.
So would you say, okay, so in our current life, do we use polar codes?
Yes, use polar codes if you ever use 5G.
Okay, so in general, do we prefer to use polar codes and then we would sacrifice time and space complexity, but to accuracy, or do we generally prioritize accuracy rather than time and space complexity?
This is a very complicated question because it's more about like it's very situational, right? It depends on the hardware you have. If you have really high-end hardware, right, you're gonna want to use polar codes because even though yes, it might take more time, it will transmit like lightning fast, right? It will be less, more reliable, less error prone, it's maximally efficient. But if you're on lower hardware, it might be much slower for you to calculate to do that recursive algorithm over and over and over again. Everything you transmit some, right?
You just said that we use polar codes in 5G, right?
Yeah.
But if I'm wrong, 5G is faster. If I'm wrong, maybe I'm just. Okay, so always 5G faster and polar codes slower.
Polar codes aren't slower; they're only slower computation. That's why they're only on some SIM cards and computers because your phone has to be powerful enough to make it faster, right? That's the idea. If your phone is strong enough to take polar codes, then take polar codes. If it's not, it might throttle, it might break. But honestly, this is a question I didn't explore too much into. So I'm gonna have to do more research on that. Explain.
Yeah, and I think maybe just to add on this idea, I read some things about this very specific time and space complexity problem, and I believe so. This work by Arikan was not perfectly ready, not perfectly complete. I think they had to deal with this issue.
They actually proved the Twitch channel capacity in like 2013, even though he made protocols in 2008. So it's very recent.
Yeah,
That's like in general, recursion is not, I would say, the best choice for space and time composition.
No.
yeah,
So I
At least the number of steps is known.
yeah,
Yeah.
but I think the idea holds.
Yeah, no,
the
that was-
idea, and so people take it and they improve it. I believe
Yeah.
that's what happened. So I'd like to know if there are more questions. So far.
First, I'd like to say amazing presentation.
Thank you very much. I appreciate that.
Secondly, the question, if you look at the diagram there, you split the number of bits and how many times until you get a single bit in each box, for each group, like you said. And to test the probability, how do you go about testing said probability?
Okay, so for each bit, if we go back. To about here, yeah. So it's kind of hard to have it both at the same time, but just keep the diagram again. Imagine each line inside of that row, each one having some probability of p. For this channel here, u plus v, right? Whenever we do the operation, we do a simultaneous operation. That's the p prime here. That's it. And then we assign that p prime to that new u plus v. And then we do the exact same with v, right? But it's times in terms of entropy. And I'm not actually sure how they do it in terms of probability. I'll have to look into it. But at least for u plus v, I know that this is what they do. I'm pretty sure here actually they use p squared. Because if you square that, that's one that's fine. I'm pretty sure I've seen that they use p squared. So what you do is when you do the simultaneous calculation, right? You're keeping track of the probability of each individual u plus v or p, and you should apply that recursive.
I believe so. I believe Ali has proven that the bit, which is the u plus v bit, gets more and more unreliable, and the bit that is just v gets more and more reliable. Well, he proved it only once. So if you go, I think, if you go to the next slide, I believe.
Yeah.
Or
The one before. Actually.
or is it the one before it?
The one before.
Maybe the one before it.
No.
Yes, exactly. So if you prove this and then you apply this, so not once, I believe, so many times, you can imagine this histogram being
0 and 100.
so going very. I imagine this would be the case. Maybe that helps with your intuition. Yeah, so one of them has more higher entropy, one of them has very low entropy, so it's reliable. So more questions.
Okay, maybe just in cases, but like, could you explain again briefly why does u plus v gets less reliable and v gets more reliable?
That's right. Okay. So u plus v.
No, just in cases.
Oh, yes, fine. I'll just repeat it. So u plus v, if we have the XOR operation, okay, the only situation where the output of the XOR flips, right, is when either v or u flip.
Yes.
If both of them flip, then it's going to get the exact same output. That's why. So we just do draw a probability tree diagram. We add up both times where only one flips. That's probability variable. So we get to p minus normalized.
Okay, actually, I understand why the u plus v gets more reliable. But what does v gets less reliable?
Okay, v1 is.
I mean, no, the opposite.
Yeah, it gets more reliable. Okay, if okay, I'll spin this once more, and if it doesn't stick, you can think of it like we have two observations of v, right? We're sending 2 bits. Both of them have some information about v, like as you can see here, which is why we technically see it once, see it twice. Like you got to know more about it, so the probability of error decreases. That's one way you can think about it. If you want the more mathematical way, which even myself, it's a bit complicated, especially as training, I have to take it for granted. So the first assumption we make is that the entropy, the total entropy when you add up the before and after is 2H.
This is an assumption.
This is it's not an assumption, it's a fact. Because you can't lose information, right? But you also can't gain it. You can't create information out of thin air. So you have to intuitively know that, okay, if I'm encoding it, I'm not changing the amount of information I'm passing through. And so I'm also not changing the entropy. Yeah. Next, we move on to the chain rule of entropy, which is just this formula. You can think of it kind of like, okay, I find U and V. So I send U plus V, for example, and then I observe V, given that I now know U plus V. You can think of it like that, like the total conditional entropy. We just rearrange this formula, right, to find the new entropy of V, and we obtain this. Now we've already defined before that the total entropy after is the same as before, which is 2HP here. That's why we plug that in there. And the new probability we know for U plus V from the previous section is P prime. So we have 2HP minus H of P prime. Yeah. Where 2HP minus HP prime obviously is greater than H of P as long as the probability is less than half, which is already a condition for biasymmetric channels. You want to know why it's a condition? Okay. It's because, okay, if you imagine the, I did not plot it, but the function for information goes like this, right? Which is log 1, wait, no, information goes like this. Function for entropy goes entropy, which is one, it's P log P plus, yeah. Sorry, it's minus P log P minus 1 minus P log 1 minus P. But basically, that's just the entropy. The entropy goes like this. It's just a perfect half circle on x-axis.
Okay.
As you increase the probability on the x-axis, the entropy increases up to a point. After that, it starts decreasing. Because if you know that P is, for example, 0.6, if you just take 1 minus that, if you just flip all the bits, right, then the actual probability is going to be just 0.1. That's it. The effective. You know, it's more likely to not flip it again. I
think what it's trying to say is that this inequality is true under the assumption that P is less than half.
Okay.
Okay. So, okay. Any more questions?
Yeah.
I'll go half one.
No, I was just confused. I think someone already answered it, but that you repeat this process, and every time the entropy gets either like it either tends to 0 or it tends to 1. And then depending of if the entropy is 0 or 1, then you will choose the indexes. And then the ones that have 1 are the ones that you choose as your frozen bits. Yes? Yes. Okay. No, thank you. Yes.
So, do you have more questions for the speaker?
More questions. Great.
This one, actually, this one, the definition wise, we talk about the distance. We can only too much. It's not a big question. Okay. Is that defined by the difference of the thing like
The number of chains.
no, what's it called? Hamish inequality something.
I mean, basically, you take the weight of absolutely.
Is it the difference of weights, or is it just exactly the difference between them?
No, it's exactly the difference, which you can model as the weight of the difference.
But let's say you have 1100 and 0011, which means that they're maximally far, or they're close.
You have what? Say?
1100 and 0011.
It means that the farthest possible.
Okay.
Yeah.
That's fine.
Okay. Perfect.
Yeah.
Thank you all for attending my talk. Thank you so much, Nelly, for helping me out with the research presentation, helping me gather resources and all of that. I couldn't have done it without him. I can't lie.
Thank you, Ali, for this very, very informative talk. So this is now the second talk already fastest. And for the final talk, we have a very interesting number theory problem. Van is going to talk to us about it. So stay with us until then. We'll start in 5 minutes. problems. But the number of questions.
No, I don't.